Everyone. Welcome back. We're now going to begin our next series of presentations. As a reminder, we're going to do it in blocks of 2 talks, and then we'll have 15 minutes for discussions. Before we get started, are there any questions or announcements anyone would like to make? Okay, great. If not, then I propose we just jump right into the talks. So Ryan, would you like to share your screen now?
Yes. Can you hear and see me?
Yes, we can. Great, thanks. And our first talk of the session will be by Ryan Stoner at the University of Miami on the evolutionary feedbacks between fluid transport and slab dynamics during subduction. Ryan, the floor is yours.
Okay, well, thank you, John, and thank you everyone for joining across the globe. As John mentioned, I'm going to be talking about subduction, specifically shallow subduction, with a focus on the plate interface, which we think of as the weak region where strain is localized during subduction. And shown here is a little schematic of that region. One of the key processes associated with subduction is that as typically oceanic plate is under thrust below the overriding plate, it's brought into contact with warmer conditions that melt at depth, where the oceanic crust can behave as a fluid source. So as it is under thrust, some of the minerals that contain volatiles are destabilized, that release fluids that can percolate upwards and then along the plate interface and can hydrate the mantle wedge. So as this region of potentially hydrated ultramafic minerals is stabilized, these minerals such as serpentine are hypothesized to grow in over time and then also potentially lubricate the interface based on both field and experimental studies. If there's any minerals that don't completely dehydrate, then those might be returned to depth. So a lot of what we've been focusing on has been what is happening at the plate interface. There's been some research on what's happening at the plate interface, sort of focusing on viscosities at the interface. And there was this previous study by Baron Becker that focused on the lubricating influence that sediment, which is thought to be weak based on experimental studies, might have on the interface, that can lower the interface viscosity and then reduce the shear stress along the interface and then potentially increase the plate velocities. This isn't something that's only based on experimental studies. We do actually see this in the field itself. Weak lithologies such as this marble and schist tend to wrap around stronger lithologies like the oceanic crust. So this has some field evidence-based reasoning as well. And the main hypothesis that we're trying to understand is disentangle the effect of fluid sources and the things that are actually produced by those fluid sources. So we're trying to understand how much of the lubrication potentially from sediments or other downgoing lithologies might not be just because the material itself is weak, but because it's releasing fluid that's then forming weak minerals such as serpentinite along the plate interface. So this seems like perhaps a simple thing to do, but it's a bit challenging to actually model because it involves some amount of feedbacks during serpentinization. So I'm showing a couple different zoom-ins of the different processes that are happening. Bottom right, we expect the plate interface to evolve, for the temperature of the plate interface to evolve over time. We expect that to then tie into changes in the dehydration, and then that might also change the plate kinematics as well. So going through these individual steps, we have the pressure and temperature plotted here on the plate interface that evolves, and then we can use something a little bit similar to what Rampang mentioned earlier and have lookup tables that are implemented in AskEffect, or we can look up how much water might be stable at different conditions, different pressure and temperature conditions, to say something about where fluid might be released. Then we can use those pressure and temperature conditions to predict the dehydration and then predict how much serpentinite might form on the plate interface. Then using aspect, we can use that to see how that ties back in to kinematics, and then see potentially whether it completes the full loop and affects the pressure and temperature conditions as well. So let's go to the setup. We are modeling an ocean-ocean setup for subduction. We're using a free surface. We used aspect 2.5 for this, and then we're solving for fluid production based on lookup tables, and then evolving the rheology and density based on those. So here's our viscosity plot for our setup. This is after a couple time steps to equilibrate the topography, let it isostatically adjust. And now let's have a zoom in on what's happening near the interface. We have different lithologies that I have set up here. We have sediments on top, then a layer of basalt below that, gabbro, which we're using different lookups for monitoring the amount of water and the density that's evolving through time. And what you'll really notice here on this one plot is as we have a function of depth within the slab, most of that water is going to be coming from, or a very large chunk of that water is going to be coming from sediments. So how are we treating that? How are we treating these feedbacks that might be forming? What we have is we start off with some amount of bound water that's shown on the bottom left. And then based on the lookup tables, we can say how much fluid is going to be released. Then we use a very simple advection scheme to just say that the water will move upwards at 10 centimeters per year. This is implemented as a Darcy field, but we just set it as a constant rate, so we aren't actually solving for Darcy flux. Then it can have three possible fates. Either it gets into a region where melt might be stable, and then we remove it from the system because we expect that any water that comes into contact with melt will just be absorbed in the melt. So that's not the focus of our work. Otherwise, we weaken the mantle wedge by 100-fold if it's not within the melt region. And then the one that's really interesting to us is if it comes into contact with the melt, with the mantle, and serpentinite is stable, then we form a compositional field for serpentinite in black. So this will become more obvious when I show some of these simulations as they evolve through time. So this is a snapshot of one of the first time steps in our models. We have on the left viscosity, on the right a compositional field that's a bit zoomed in. And you'll notice a couple of things that are happening on this compositional field that's focused on the plate interface. There's some free water that's getting released from the downgoing plate. And then we have a melt field just to show where water is getting removed. As we progress forward, then you'll notice this black band of serpentinite that forms. And we have a depth-dependent plot of how much serpentinite is forming with depth. I say above 10 weight% because we expect there to be some rheological threshold where this serpentinite rheology kicks in. We don't expect it to happen for smaller amounts of serpentinite that aren't plotted. And then later on, this is going to be a bit more familiar to other people. As the plate descends further, then it's going to interact with the transition zone, with the 660 transition zone, and start to slow down. So that's why you see the slowdown in velocities. Plotting those velocities up, these convergence rates, we're plotting on the y-axis the convergence rate, and then on the x-axis, we found it was really important to plot up net convergence. So this is the amount of plate that's been consumed over time. And you'll see that there's this peak in velocities during this free sinking phase, which we have as a Roman numeral 2 here, and then this slows down later on. I want to bring your attention to the serpentinite column on the far right. We do see that there's some amount of serpentinite that's getting dragged down as a function of time. So that is actually some process that we're able to capture here. But what we really wanted to understand is how much does serpentinization affect the interface. So let's plot the amount of cumulative serpentinite and instantaneous. So this is this represents the cumulative is the total amount of serpentinite that was formed over the whole model run, and instantaneous is how much is there at that point in time. So the difference between the two is actually a measure of how much down dragging there's been of the serpentinite. So the cumulative includes stuff that was stable at one point, but then gets dragged down as a function of time. And the main thing that we really wanted to do is to compare what happens when you keep everything equal, but you change the hydration state of the incoming material. So in this case, the sediment. So we have a case where we include the maximum amount of water in the sediment. We keep everything equal for a second case where we have no water in the sediment, but we keep the sediment rheological properties the same. And you'll notice here that there's a difference, unsurprisingly, in the amount of serpentinite that gets produced over a certain amount of time. These are different time steps, but they're the same amount of, they're the same numerical time steps. So that's important to note. Then we have a couple other cases, an intermediate case with 4% water, and then a case with no sediment whatsoever. So sediment is causing a lubricating effect based on the rheology of sediment, but there's also an effect from the water as well. So let's plot up the ingrowth of water. So you see these differences in on the left of the amount of serpentinite that's coming into the system. And that's also going to show up in the convergence rates as well. So what you see here is that the highest, the setups with the most water in the system have the highest convergence rates, but then they're a bit slower if you don't have any water, and then they're even slower if you have no sediment as well. So there is some effect from this serpentinization here, and it seems to be a very decent chunk of this effect. This is mostly based on the fact that we're using meaningful values for the friction of serpentinite. So we also did things such as changing, if I can, oh, there we go. Changing the friction of serpentinite to test this effect, how much it changes things. My mouse is being very sticky. Okay, so we changed that, and then that changes the convergence rates as well. So this effect is modulated based on how weak the serpentinite is, unsurprisingly. So further work from experimentalists on serpentinite rheology will definitely help clarify the magnitude of this effect. Going into take-home messages, what we do see is that serpentinization is lubricating the interface, which leads to faster convergence rates. There's a lot of other variables that can affect convergence rates. So by no means are we saying that this is the thing that affects convergence rates. It's just one of the things, perhaps. And then there's much more work that can be done now with aspects, expanded capabilities, looking at more sophisticated models of fluid flow than just our simple advection. We expect some amount of fluid to also go along the interface. So there's really a lot of future work that can be done with this that can really add much more sophistication than we have here even. We do see that the intermediate to mature phases are most affected by the serpentinization. That just means that there has to be some amount of time for serpentinite to just grow into the system. So that's explained by that component. And we also expect sort of bringing it all together. One of our main takeaways, despite the complexity of the lookups, is that we expect that lubrication at the interface that has been hypothesized to be due to sediment might not only be because of the sediment itself and the sediment itself being weak, but because the sediment is hydrated, that releases fluids, forms weak minerals, and then that can lubricate the interface. So with that, thank you for your attention, and I'll take any questions.
Excellent. Thank you, Ryan. If anyone has any questions, feel free to put them in the chat. But then, as a reminder, we'll have a 15-minute block for questions after the following talk. And with that, Ryan, would it be okay if Petra began sharing now?
Hey, hello everyone. I'm really excited to present. Thank you for letting me to do that. I will speak about porous melt flow, which is a process that is typically invoked to explain melt accumulation beneath mid-ocean ridges in the mantle. But I will here speak about it in the frame of continental crust. Usually when we think about melt transport in the continental crust, we think about brittle structures like cracks that open, they are filled in by melt or magma and form dikes. And this is, of course, very, very typical, but it's more typical in the upper portions of the crust that are actually prone to brittle fracturing and that are under solidus temperature. While when we get to deeper parts of the crust, we see something different. We see partially molten rocks that are now called migmatites as they solidified, and they have a banded structure which is the result of segregation of the melt and solid. And we can see also a lot of ductile deformation and different kind of folding and things like that. And it is somehow assumed that melt moved through these rocks as well, somehow, but it's really difficult to see it because the rocks themselves are very complex. But there are also different kinds of migmatites that were observed, namely in the European Berescan Belt, in the Bohemian Massif, and also elsewhere. And these rocks, they originally also had banded structure, but this structure formed during the solid state deformation and metamorphism. And these rocks lost this structure actually due to melt that flew through these rocks. So we can see that there's at a micro scale, there are places that crystallize from melt in these rocks, and the more melt we observe, the more isotropic they look. And finally, they look like granites, in fact, although at any moment there was not more than some 10, maybe 15% of melt in these rocks. And importantly, the composition of these rocks also changed due to the melt presence, because there are these rocks that contain more melt are more silica-rich and iron-rich than the rocks that contained less of it. So we have some evidence of melt flow through rocks in the continental crust. We can see that this process took millions of years. And also, here on the microphoto and here on the map of different minerals, you can see these red regions. They are places that were interpreted to crystallize, that they crystallized from the melt. And you can see that they are really dispersed. They are located along grain boundaries. And so it looks like that the melt really moved along grain boundaries. So now we have some evidence for melt flow through continental crust. And the question is when this can happen and what are its effects on the composition of the crust, on its rheology and so on. And it's an important question because there are large areas also today in continental crust that contain probably some percents of melt. Like for example here, you can see a cross section through Himalayas and Tibet. And these orange regions were interpreted as they contain some melt based on their electric resistivity that is low. So our goal was to simulate numerically melt flow and study its effects on the continental crust. There are different ways to study it, of course, and we decided to build up a model that would represent a cross-section through thick and hot continental crust. We assumed that the material deforms viscously, and we model it as a two-phase material using the two-phase approach that is already implemented in Aspect. So the melt flow through the solid is governed by the so-called Darcy's law, which says that the flux of melt through solid is proportional to the Darcy's coefficient, which is the ratio of permeability and melt viscosity times pressure gradient that drives the motion. We also simulate temperature evolution, melting and freezing, and evolution of composition of solid and melt. And these two were implemented in a plugin for material model in Aspect. So how is it with melting? So this is very simple, parameterization of melting using solidus and liquidus temperatures. And the melt fraction is then calculated from using the lever rule. The solidus and liquidus temperatures, they depend on composition. This is just a scalar variable in our model. And when I will speak about it, I will say that something is enriched when there's more components that easily melt, they easily go to melt. So that means that enriched material will have lower solidus than some reference material, and the opposite is for depleted material, which has a higher solidus. The model domain will be 50 times 50 kilometers, and it will be, in fact, a closed box from sides and from the bottom. So it will represent some internal central part of a hot orogenic crust, like, for example, in Tibet. It will be initially subsolidus, so there will be no melt at the beginning, but then we will prescribe some temperature anomaly at the bottom boundary, which will start to increase the temperature and melt the material. Yeah, here I will show animation with the results of some reference model that has parameters relevant for microscale porous melt flow. I mean material parameters like the Darcy's coefficient or viscosity of the solid. And you will see here the evolution of melt fraction and isotherms. And to the right will be the composition. Yeah. So you can see that there's a partially molten domain that grows. The melt moves towards the surface because its density is lower than the density of the solid. But it's also the solid that moves together with the melt, in fact. So we have an upwelling in the center, downwellings on the sides. There's a temperature increase in the middle crust. And you can see inside the partially molten domain, you can see some waves or some blobs, or how to call it, of increased melt fraction, and that are porosity waves. And in composition, you can see that the composition changes. So in the middle crust, we have enriched composition, and the lower crust is depleted. Yeah, after 5 million years, we switch off the temperature anomaly at the bottom, so everything solidifies, but the compositional variations, they remain there. Here's just a few snapshots. You can see that the melt fraction is somewhere between 10 and 15% in the partially molten domain. You can see also the velocity. So in colors, it's the relative velocity, and it's mostly less than 1 centimeter per year. Here it's a bit more, but it's a rather slow process, but it takes millions of years. So over the time, you can see that the compositional variations still develop, and it has an important effect. Of course, that was just one model. If we change model parameters, we can get different results. So here, for example, we choose higher Darcy's coefficient, so the melt can move more easily through the solid, and it can therefore take more composition, like change the composition more efficiently. And you can see here also these green points, and these are places where the melt overpressure is high, so that some cracking would be likely in real rocks. But we don't model this because we have only viscous deformation. On the other hand, if we make the solid deformation easier, for example, by lowering the viscosity of the solid, we would cause more convection in the model, and there will be more mixing and things like that, and there won't be so much compositional changes. So we can play with the model a lot, and we discussed this in a paper. So I would refer it to a published paper. And the main point to me was that even for quite realistic parameters, we can get melt flow that during millions of years, it can affect the composition of the crust. And the second point was that it's really sensitive to parameters, what we choose, meaning that even like small changes in permeability or in viscosities can have large effect. Okay, so this model is fine, but it has some problems. And one of the problems is the melting parametrization, which is very simple. So it's just linear. And the problem is that if the material is enriched, as it is in the middle crust, we can get melting at very low temperatures. So like here, we have melting at less than 600 degrees. And that's not realistic. And we therefore can't use it for some more realistic tectonic setups. And so we decided to change this and implement a more realistic description of melting, where we directly link the composition to the water content. So now, because this already has some physical meaning, we can define the liquidus based on experiments, for example, and solidus based on thermodynamic models, and then just simply calculate the melt fraction using the Leber rule again. This is still very simple parametrization, and it's easy to implement, but it gives us a much better estimate of melt fractions. So here's just an example how the result looks like with this different parametrization. Again, it of course depends on many parameter models, many model parameters, but in the end, we can get similar simulation, similar results as in the reference model with a large partially molten domain. And the nice thing is that here we have well-defined solidus where the material can't really be molten at low temperatures, lower than some realistic value that we define. So here's just snapshots. In this particular model, the velocity of the melt as it moves through the solid is somewhat lower than in the models before, but it depends on the parameters of the model. So this is something to be tested. And the good thing is that we can use this parametrization to build more interesting models with tectonic forces, for example. And one more point is that in this model, we can use a reasonable melt viscosity, because now the melt viscosity in the first round of models, it was a free parameter. But here we can define it directly, because the melt viscosity depends on the water content in the melt and on temperature. And through the water content, it also depends on pressure. So for pressure and temperature, we can calculate melt viscosities. Of course, there are different models depending on different experiments, but you can see that they agree that the melt viscosity decreases with increasing pressure, which means that the ability of melt to move through the solid increases with increasing pressure. That suggests that melt flow at the microscale might be important in lower crust at high pressures, while in the shallower crust, it might be rather some melt segregation into macroscopic features. And now we can also compare it with the data. So for the different research, for different publications that would report microscale porous melt flow in continental crust, and you can see that they mostly cluster at higher pressures, like more than 1 GPa, except this one, but these rocks actually also came from large depth. So it's quite possible that the melt flow in these rocks also occurred at higher pressures. So it's just a suggestion. Of course, this is not a proof, but it tells us something that we may look into this if really the microscale melt flow isn't dominant at high pressures in deep crust, while shallow levels are dominated by different processes. And this is just a very quick summary, but I think I can thank you for your attention, and we can discuss it later. Thank you.
Excellent. Thank you, Petra and Ryan, for the excellent talks. Guys did an excellent job on timing too. We're right at the midway through the hour, and now we can open it up for general questions for the next 15 minutes. Yes, Daniel.
Yeah, great job. Both talks were really, really interesting. My question is for Ryan about you said you were using the Darcy field, but you're imposing a uniform like 10 centimeter per year uplift rate. What like, do you know what porosity that corresponds to? Like if you were to put it into the Darcy velocity equation, and then also, was there like convergence issues? How come you're doing that instead of using the Darcy velocity advection method?
Yeah, so this was we started using this before a lot of the functionality was fully out there for the Darcy advection method. So it is a Darcy field, and it's using the Darcy fluid advection method to move upwards. Can't say off the top of my head what porosities that would correspond to. Just know it's been used. Similar values have been used in previous studies, so it should be a relatively low porosity there. Otherwise, yeah, for people who are doing it in the future, there's a lot more sophisticated functionality now in Aspect. So, thanks to you. Hope that answers your question.
Thanks. Yeah, it did. Thank you.
Yes, I'm Prajakta.
Hi. So I have a question for Petra. So like you discussed about like in your model setup, I have very specific question related to the melt. So because I'm working on the melt as well. So in material model, like what is the density contrast you're using between the solidus and liquidus? That's my first question. And the second thing, like what temperature profiles you're using basically? Like how are you like setting the temperature profile? Yeah.
About the difference between the solidus and liquidus. Yeah, I changed this as a parameter of the model. So I tested different differences between solidus and liquidus, starting from 200 to 1000. But then I realized that it would be actually better to have some more realistic parameterization, and there in the new one, sorry, it really depends on the yeah. It's not one value. Then it's a real loop. And the other one was sorry, what was the other question?
The temperature profile I was asking, like
yes, the initial temperature
geotherms.
profile.
Yeah, basically geotherms.
I had some. I calculated some steady state profile using because I had there like radiogenic heating, and so based on this I calculated a steady state profile. And as the crust is very thick in the model, it's 50 kilometers, then it was rather hot at the bottom, but it was still subsolidus. It was almost 800 Celsius at the bottom of the domain.
Thank you.
Fritz.
Hi there. So I had a question for Ryan. When you were decreasing the amount of sediment in your model, I saw that it decreased the angle. I was kind of expecting it to slow down. Like, did those models take longer to complete? Because I would expect with that increased friction, right, that it would slow down subduction.
Yeah. We were running all of the models for 50 million years. So the duration for all of them is the same. It does slow down subduction. So having the lack of a sediment is slowing stuff down. Yeah. So it is going slower. We were plotting all of them at the same distance of convergence because we wanted to standardize for the amount of water that's coming in to the system. Yeah, so that's why. But it does go slower. That's right.
That makes sense. Sorry, follow-up question. That angle was decreasing as well, and you said that you had a purely buoyant, like percolation of water up through the material. Do you think that that had a kind of positive feedback loop, whereas as the angle decreased, you got less material into the overriding mantle, and that decreased lubrication further?
Yeah, that's a good question. I'm not entirely sure, but I would lean towards yes, that would also have an effect in it as well. Yeah, certainly everything in those models, I didn't show the pressure temperature evolution just because that's more complexity, but they do get quite cold with the sediment over time, and it does lock up quite a bit. So I would expect that part of the process, the fact that it's moving more slowly and that it's locking up and cooling that way is probably contributing to this as well.
Cool, great models. Thank you.
Yeah, Julian.
Yeah, really cool talks, both of you. Thank you. I do have a question for Petra. So you showed these green dots that show where you said basically the fluid pressure is high. So that's places where you might expect some cracks opening up. And so I was wondering if you had looked at basically just where is the fluid pressure above some threshold, or is it also sort of where in the model is the brittle ductile transition? And right, so I mean, you could in principle just say if you, right, it's of course really hard to put in the actual failure into a model with melt migration, but one could ask the question, right, with the fluid pressure, am I actually above the yield strength, or would I expect to have failure? So I was wondering how you computed that.
We just took the places where the fluid pressure is above some threshold. We didn't compare with the yield stress or something, because we knew that we wouldn't anyway. Yeah. Also because the model is just a closed box, so there are no tectonic forces, and I think it would be very different in a like more realistic setup. So we didn't go into more details.
Oh yeah, that makes sense. Thank you.
Sorry.
Other questions? Yes, Renee.
Yes, I do have questions, but there were also a few questions in chat. Would it be worth looking at them and discussing them for everyone so that we don't have lengthy chat discussions? Might be simpler. So the first one was from Michael towards Ryan, I think. What initial friction angle did you use for the sediments and for the serpentinite? And any idea how much serpentinite and sediment-filled free water decrease the shear stress along the interface?
So the initial friction angle for the sediments was quite low. It was 4. And then for the serpentinite, we have, for the reference model, it's 2, but we vary it from 1 to 4, and then in recent stuff that I ran on my own up to 6 as well. So those are fairly low values, but there's reason to think that they could be that low. And then the other question was the shear stress. I remember looking at this a while back, and it was about halved from having the serpentinite in there, but that's a good question, and definitely something that we're going to work on quantifying more fully.
Thank you, Nestor.
And oh yeah, go ahead. And I think the second question was maybe already answered in chat, so I can skip that. I actually had a question for Petra, and that is about the solver convergence behavior in your models. I remember that in two-phase and full two-phase flow models, this is often a problem to get proper convergence. Did you see that as well? Especially since you're also like in the crust, like large viscosity contrasts in the model.
Yeah, I think I had some problems, yeah, with numerics in this, and I think that particularly I had problems with the velocity of melt, as it gave larger errors, and somehow, yeah, this was a problem. But I tested like different allowed errors for the convergence, and I didn't see very much difference anyway. So even
so playing with the solver tolerance was enough.
Didn't help. Didn't change. Yeah, didn't change the result much. So I even was like doubting if it's not somehow problematic that it takes into account also the melt velocity error, and that this may somehow spoil the convergence, and it can't be helped somehow. Maybe I don't know. It's just a guess.
I don't think that would be the case. I don't remember the details very much, but I think the melt velocity is actually computed as a post-processing step in the way that two-phase flow solver is implemented. It's also an additional pressure. So we have the normal velocity and then two pressures in that system. But of course, because of the melt velocity, materials get advected in different ways, and so it still influences the solution. But great to hear that it was possible to get it to converge. Thanks.
Petra, I have a quick follow-up question for Renee, and then I see Sarah has her hand up. I was wondering, what timescale did you use for the reactions? Because what we found for other models, like related to hydration and not melt, but that can have a pretty big impact on the convergence behavior as well, just as you're changing, just because that affects the amount of porosity, like the timescale over which you're developing, changing the porosity.
I didn't play much with that. I think I played with that like initially, but not then during really producing the final models. I don't remember the number, but it's like 1,000 or 2,000 or something. And yeah, I don't know. I should have tested this. Yeah.
There are many parameters. There's so much to test.
Yeah.
And
so should it affect the convergence or the result, like both?
Wei found it affects both.
Both. Okay. Thank you.
Yes, Sarah.
My question's for Petra. I was wondering if you think there are any analogous melt transport processes happening in the lithospheric mantle, like just below the region where you're modeling, if you've thought about that at all.
I don't know. I would say that it's different because where I look in the crust, it's frankly, I don't know. I didn't think about this. No. But it's studied for the mantle, for beneath mid-ocean ridges. There's plenty of literature about that. But I think it's different for the lithosphere, as it's much stronger. Yeah.
Other questions for Petra and Ryan? Okay, if not, again, there'll be opportunities tomorrow where everyone can ask follow-up questions. But I think now is actually the perfect time to move on to the next set of presentations. Petra, when you have a chance, would you be able to stop sharing your screen? Great, thank you. And our next talk will be given by Liang Zhu. And Liang, feel free to start sharing your screen when you're ready.
Great. Great. Can you see my screen?
Yes, I can, and the floor is all yours.
Great. All right. So thank you, Jiang. Today I'm gonna happy to share some preliminary results on the climate and reef setting interaction. So continental reefs are characterized by the regional extension, upwelling of the mantle, and development of border faults. So leading to very unique topography where the footwall of the border fault has uplifted, the hanging wall has subsided. So as summarized by Wolf et al. In 2022 here, you can see the reef flanks would experience erosion and sometimes orographic effects here. And the basin here would have the sediments and the reef lakes. You may find the thickest sediments and also the deepest lake on the continent in the reef settings. So reefs are one of the key settings where climate and tectonics strongly interact. So let me see. Okay, it works. So thanks to the development of coupling between the landscape evolution model and the geodynamic model, there has been growing interest in understanding how climate-driven surface processes could influence rifting and crustal deformation. So for example, Newhurst et al. On your left, you can see here, look at the role of the erodibilities of the different phases of the rifting, from initiation stage to the continental breaking up in different cases like white rift, asymmetric rifts, and they look at how the sedimentation could change through localization in those different phases. And Olive et al., which is summarized in this figure in the middle, following our work in 2014, highlights the role of the erosional efficiency on the development of secondary border fault. So the erosional efficiency can be measured directly from the topographic map as a great validation to the modeling result. So on your left, you can see this work by Wolf et al. Also look at the correlation between the stream localization and the sediment flexion. So there you can see this is the sediment flex and the time-dependent sediment production, and found that the maximum, the highest sediment flex right here can post-date the peak of the uplift on the reef flanks. So beyond the crustal deformation, climate-driven surface processes can also modify or potentially modify the magmatism during rifting. Continental rift is always associated with volcanism and magmatism. For example, Starting et al. Showing that the erodibility in longer term could modulate the mantle melt. In shorter term scale, Xue et al. Shows that the lake level fluctuation has the potential to impact the mantle melting value. And more recently, on your right here, Claric et al. Shows that the deglaciation in places like Yellowstone and Iceland may enhance mantle melting and promote CO2 degassing. So they create a feedback loop that the enhanced CO2 may further encourage deglaciation. So of course, there are many other studies on this topic. Here are just a few, but so you can see this rifting and climate-driven surface processes are deeply interconnected. Today, I would like to focus on only one aspect. How do erosion and the deposition may influence stream localization in an oblique rift settings? We choose oblique rifting because like 70% of the rift systems that eventually leading to continental breaking up since Pangea shows a certain degree of obliquity, as suggested by Broom et al. In 2018. And so for the orthogonal boundaries, which take only like 8% of total plate boundary lengths. So our main question is, to what degree can climate-driven surface processes, including erosion and sedimentation, could impact stream localization in an oblique rift setting? So let's quickly go through the model setup. We run the model for like 30 million years, and the top boundary is controlled by Fascape. And you can see our wake zone is right here. It's 45 degrees to the direction of the extension, which is from east to west. So I'm gonna show two cases, two scenarios with different precipitation rate. One is 0.01 meter per year, another is 2 meters per year. The effects of the precipitation would be reflected in stream power law as a part of a K, the erodibilities. And also please note that there are 3 transects over here, 1, 2, and 3 across our model domain. We're gonna extract some data from those transects. So now let's look at the first part of the result, which is topography and the local relief. So in the low precipitation scenarios, we can see the well-defined drainage divide, which is right here, even at last at you can see that at last step of model, relatively higher local relief and deeper rift basin. And also we can see rather small rift drainage basins within here. But under the high precipitations, we can see a lower averaged elevation due to more intense incision on the rift flanks, and the lower the elevation by about like 1,000 meters. Additionally, you can see the increased precipitation leads to large drainage areas and the forming of those large delta. You can see right over here, 2 of them, and also the migration of those depth centers as the sediment is more effectively transported. So you can see the large change in topography, and how does this difference in surface processes impact deformation? So here we're looking at the cumulative plastic strain. So we can see both scenarios at an initiation stage while forming those E-echelon structures, which are those paralleled smaller segments along the rift. However, the way the strain localizes later will be different. So in the lower precipitation case right here in the upper panel, you can see the structure gradually linked up with the intra-rift fault and eventually forming some major faults that is perpendicular to the extensional direction, like what you see here. However, in the high precipitation cases, those E-echelon structure will rapidly connect with each other and forming some border faults. As a result, you can see the development of the 2 dominant border fault across the model domain, aligned with parallel with the pre-existing wake zone. So the difference of the deformation would eventually impact the crustal and lithospheric thinning, which is showing over here. This is evolution of the crustal thickness. And you can see in the lower precipitation scenarios, we observe in the later stage a gradual rotation of the most thinnest part. At initial stage is almost perpendicular to the wake zone, but by the end, the rotation reached about 20 degrees, which is right here, close to the perpendicular direction to the extensional direction. So it highlights how the surface processes can influence the lithospheric dynamic over longer term time. So next, let's look at those transects. We have 3 transects over here. And you can see from north to south and 1, 2, 3. So we are gonna look at how the data changes through times along the transect. So for example, we have this transect 1, and we plot that change, the data change through time. This is sediment thickness. The x-axis is time from 2 million years to 30 million years, and the y-axis is distance along this transect. For example, here, it shows that 3 million years, the thickness of the sediment starts to grow, but at 18 million years, the change of sedimentation rapidly increase, almost within this weak zone, which is highlighted within of those white dashed line. And also, this is a map plot of the spring rate. We can also see how the spring rate change through time. With that, we can compare the difference between the two scenarios along the three track sections and the high and the low precipitation cases. So let's look at that. So first, you can see during the first 10 to 12 million years, both cases produce a relatively narrow rift basin. And but in lower precipitation cases, after that, we can see the significant migration of the depth center from this side to more close to the wake zone, and in both north and the south sectors. However, if we're looking at the high precipitation cases, the sediments and the sediment thickness almost always concentrate in the wake zone. On the right, there are two profiles along those transects. You can see that even clear. For the low precipitations, you can see the migration of the depth center from your right side to the center. And also that is impacted by the fracture over here. And also if you are looking at the high precipitation case, you can see much deeper and more symmetric concentration of the sedimentation. So this also would impact the stream localization, which is shown in next slides. So we can see for the first 10 million years, both cases showing like similar small stream pattern, which with the stream coalescing within the rift basin over here within the white dashed line. And after that, in high precipitation scenarios, stream localizes on the border fault, two of those border faults, forming a full graben across all three transects. But after about 20 to 20 million years, one of those border faults will be abundant and half a graben will form, like here, to forming a half graben for two cases. But in the low precipitation scenarios, stream manifest for the echelon structure. This alternating of the high value of the spring rate is expression of the echelon structure, and several of the echelon structure will survive to the last stage of the rift evolution to forming the fault we see on the last stage that is perpendicular to the extensional direction. So this difference and also the interaction between erosion, sedimentation, and stream localization can be explained using this diagram. Since rift faulting require energy from far-field extension, which is converted to like elastic strains, fractional resistance, and gravitational potential energy, GPE. So as the border fault grow, it will has the increased footwall relief, and those relief will increase fractional stress, driving the stream migration from the border fault to other directions, and which is more energetically favorable. However, erosion of the footwall and deposition on the hanging wall will make the topography more smooth. So it will reduce the GPE buildup, allowing for border fault to accommodate stream even longer. So in the lower incision and deposition case, it will preserve higher relief and increase the variation of GPE and the vertical deviatoric stress over here. This variation in deviatoric stress rate will promote the migration of the stream to develop some of the secondary faults along the rift profile over here. So, but in the high precipitation case, the deviatoric stress tau here is more flat, more widely distributed. So that's the explanation of the relationship between the erosion, deposition, and the development of waterfall. So to some key result is that we found that strain erosion and the sedimentation would promote a longer life of the border fault and half-graben development for especially away from the center of the oblique rifting. And the lower erosion, the sedimentation would promote echelon structure, and it can survive to the last stage, forming some fault that is perpendicular to the extensional direction. So I think that's it. Thank you for your attention.
Excellent. Thanks for the great talk, Liang. And we are right on time for the next talk. If anyone has any questions, would like to begin, please feel free to put them in the chat. I'll have a discussion section in 15 minutes. And then Argelia, would you like to share your screen and begin the presentation?
Yeah, sure.
Excellent.
Thank you.
And the floor is all yours.
Okay. Okay, thanks. Well, first of all, thanks for the invitation, and well, everybody, thanks for being here. My talk is a short summary of the recent model or recent models that I performed mainly in collaboration with John, but also with the support of the Italian National Research Council and the National Institute of Volcanology and Geology in Italy. And well, the title of my talk is Unveiling the Origin of High Deformation Rates in Holocene Faults using geodynamic modeling. And as the title said, the object of this talk is some Holocene faults. But where do we have these structures? Well, these structures are part of an active volcanic caldera that is called Ischia. It's located in the south part of Italy in an island. And the main importance of this active structure is the relationship with the high seismic risk that has been well registered during the last 3 centuries until a couple of years ago. Here, the seismic risk is one of the largest in the Italian catalog due to an extremely low depth of the fault motion, the presence of dense urbanization on the faulting area, and also the vulnerability of the buildings. Well, to be in a general volcano-tectonic context of any caldera, because this was, of course, very important as a starting point for the numerical model. I'll start by saying that calderas are depressions that are associated with the withdrawal of a magma from a chamber that induced the collapse of the caldera roof and creates a depression with also the formation of the ring faults as structural boundaries. In the case of the caldera of the study of Ischia, this picture represents the first stage of the formation of this depression. Then the caldera is filling with the different deposits, volcanic products and so on, that may cause a subsidence stage, which in combination with the changes of the pressure in the magma chamber, because maybe we have an injection of a new magma body or the depressurization, but because of any volcanological phenomena, this in combination with the presence of hydrothermal system and the presence of the previous faults, a vertical motion can displace outward the caldera floor, leading to a resurgence phenomena. And for Ischia Island, this is the case that we are gonna study, that I'm gonna talk about during all this talk. In the case of Ischia, a localite model has been proposed as the main source to explain that this resurgent activity that has been happened during at least the last 33,000 years stress out the lower crust of the Ischia area, leading to the occurrence of the many fractures and decreasing the stiffness of the rock that helps, of course, to drive the magma outward, ending up in the uplift of the resurgent block that in this case we are going to call the Pomeo Mount. But besides the uplift of this resurgent block, also the presence of an east and west normal fault system was developed in order to accommodate all all of this vertical displacement after the resurgence of the caldera of approximately 1 kilometer. And these faults are those that are linked with the occurrence of the earthquakes that have struck the north part of the island. While these structures originally were formed, and it's well documented that they were the result of the resurgence activity due to the magma body, the formation or the current deformation and the rapid and characteristic slip rates that are typical of them are still very debated about the origin of what is the source of the main fissure that caused this behavior on these faults. So based on this, my objective when I started to use aspect was, first of all, to examine how the regional tectonic stress, which control most of the faults on the area surrounded the caldera, influence the current deformation, faults. And also, I wanted to understand how the presence of this magma body, this laccolith, perturbs the deformation of these structures. And finally, also explore an scenario similar to this second point, but instead of having a movement upward, having a movement in an opposite direction, like simulating a subsidence stage, because this has also Weil proposed. So getting back to this figure that represents the conceptual model of my numerical model of the caldera, if we zoom in these faults, we can see that the arrangements of the faults form a structure like graben that has displaced different blocks, especially downward. Based on a stratigraphy correlation that I supported with the analysis of the different drilling data and radiocarbon dates, I could estimate the cumulative slip rates, especially in the border faults of this graben. This was with the objective to have a geological benchmark to compare the results of my numerical results. Well, in the following slides, you are gonna see a lot of these numbers, no? 29.2 millimeters per year for one of these faults and 5 millimeters per year for the other fault, which are the slip rates. So I set up a two-dimensional instantaneous model with a dimension of 11 kilometers per 3.5 kilometers in depth, using a free surface and imposing 3 different velocities boundary conditions to simulate the three stress fields that I wanted to test. But, well, I'm gonna mention the numbers in the following slides. So different important implications were considered. I needed to consider some specific features about the area that I'm studying, because having a volcanic environment means to have a thermal anomaly that also affect the behavior of the rocks. Also, we have hydrothermal alteration that affects the rock mechanic properties. First of all, I took all the values, especially the cohesion and the friction angles, also the density, well, that didn't change so much, from all the literature that consider the presence of volcanic rocks with some hydrothermal alteration and rocks similar to those that we are having in the area. Then, if you see this graph that represents the geothermal gradient of this of the Ischia caldera, we can see that we are reaching high temperatures values at really shallow depths. That's why the brittle ductile transition zone is located at around from 2 to 3 kilometers, where the pure elastic condition may persist at this depth, with a temperature approaching to the elastic limit at the same depth. So I use different resolutions to ensure the presence, to have enough elements inside my faults, given that they were not so wide. And first of all, my first combination of refinements of one global and adaptive refinement gave me a resolution of 15.6 meters inside the faults, but then I managed to increase this number of elements and increase the resolution of the model up to almost 2 meters of resolution. So we have a good number of elements to solve inside the structures. So now here we have the first model that explores the effect of the tectonic stress. For this, I impose a left and a right velocity of 0.35 millimeters per year of extension that is equivalent to a well-known sectional strain rate of 10e-15. That is characteristic of the Campanian area or the Tyrrhenian Sea, where the caldera is located. We can see different things based on these results. Although most of the highest values, although most of the deformation is located on the faults, even the deformation is in the shallow part of the faults. We can see that this extensional stress affects either the resurgence fault, but also a little bit the ring faults. However, if we use these values of deformation to calculate the slip rates, we can see that the deformation is not enough to reach the values of displacement that we already know, these of 5 and 25 millimeters per year. In here, in blue, in blue letters, you can see how the values are too low in comparison with my benchmark. Of course, there is a deformation imposed by this tectonical extension, but it's not enough by itself. So for a second model, the effect of the roll of the magma body was simulated by imposing not only the left and the right velocities like in the previous model, but also a vertical velocity at the bottom of the model, which represents the resurgence velocity. We can see how the strain rates are well localized and in a better way inside the faults, reaching deeper limits, deeper levels, sorry, and distributed basically mostly in the resurgence faults and almost nothing on the ring faults. So this means that this stress field doesn't move, let's say, the ring faults. When I calculate the slip rates based on these velocities, I got, this was pretty nice to get basically the same slip rate for one of the faults and a little bit higher for the second one, but the difference was 2 millimeters per year. This velocity profile is very interesting, given that it not only represents the similar asymmetric topography that characterizes the resurgence block of the island, but also we can see that the maximum magnitude of the velocity is not the same as that I impose at the bottom of the model. This difference between these two velocities can represent that the deformation when you have a magma body that is moving up in upward movement dissipates the deformation also in a way of ductile deformation. So in here we are looking at the velocity at the top of the magma chamber. This can be also another geological benchmark if we consider that this velocity on the top of the magma chamber can be the same as the velocity of the resurgent block. So we know the difference of the height by the time that occur all the resurgence. So the third model that I developed was based on the idea that the activity of these east and west structures was due to a phase of subsidence of the island that has been proposed to be at 5 millimeters per year. So in this for this model, basically I did the same configuration like the previous model, but with a negative velocity, considering the value of 5 millimeters. Well, in here also the deformation is well localized on the resurgence faults. It's similar to the previous one. However, one of the borders of this graben doesn't show any deformation. Important deformation is almost zero. And the most important thing, when we calculate the slip rates, they don't match with the ones that we use as a benchmark. So to conclude, I have another one. Additionally, I'm gonna get back a little bit about something that I think that is so important to mention. Additional to the analysis of the stress source that I lead to firstly, to concentrate the deformation along the faults. One important factor that I consider was the degree in which I weakened all the faults. To simulate the plastic strain weakening, I linearly weakened the cohesion and the friction angles of the rocks, accumulating a plastic strain of from 0 to 1. And I tested the different factors of this weakening behavior by doing 10 times, 50 times, 100 times, and 1,000 times more weak. Although the most exaggerated values show a good localization of the deformation inside the faults, it's unreal to think that these values, especially that these values can be true, especially when we already have adjunct models of the rock that is already reduced by the effect of the strong alteration of the rocks because of the volcanotectonic environment. So the factor that was more logic to show, and that also show the best fit and match with the slip rates that I obtained, was just to weaken the structures by 10%, by 10 times. So for just to conclude, well, I proved with the models that the regional tectonic stress alone cannot produce enough deformation on the fault structures. It has to be in addition to the uplift of the magma chamber in a stage of the resurgence, not subsidence movement. And also the plastic strain awakening helps to localize the deformation more accurately within the fault structures. However, this approach or these variables must also have to consider other parameters such as temperature, alteration, rock stiffness, depending on the specific area or the geological environment that we are studying. Thanks.
Great. Thank you, Argelia. And then we now have about 12 to 15 minutes for questions. And so I'll open the floor. And thanks again to both Liang and Argelia.
You're welcome.
Yes, I see Sarah, your hand is up.
My question is for Argelia. That was a very fascinating application of aspects to this problem. I was wondering, when you varied the plastic strain weakening factor, were you finding more consistent results when your faults were weaker, which would be consistent with like the hydrothermal, volcanic setting, and that there's fluids on the faults in those regions? I lost you on my camera. Where are you? Oh, there you are. Okay, there you go. Yeah.
Well, definitely, I found a more consistent result when the faults were weaker, but also since the setup of the model, I consider to have in this case, well, the mechanical properties according to altered rocks, not fresh rocks, because in most of in some models that I found, like in volcanic areas, that was one thing that I've noticed, that they use the cohesion and the friction angles of a rock that you analyze on the lab. That is, of course, like super intact, no, without hydrothermal alteration. So yeah, I think that I consider the fact to weak the fall was a key element, but also the initial values of the properties of the rocks.
Okay, thank you.
Oh, sorry, Anne.
Hi, I have a question for Liang. Very cool simulations. I was wondering, so the precipitation rates that you showed, they vary quite a lot, right? It was 0.2 to 2 meters per year. And I was wondering what, and you see different tectonic evolution. So I was wondering whether you can compare your results to rift, like actual observations from rifts, whether you've already looked at whether you can see those different evolutions in natural examples. Sorry, that was my question.
Great. Thank you, Anne. It's a really great question. Actually, we're trying to find the proper location to test this hypothesis. But you know, that depends on how we can find good validations. I think for now it's a little bit difficult to find, like, in such a longer term scale. We can find some studies working on drainage basin average cosmogenic dating that's part of the drainage average erosion, but it's not like in million years, like we're modeling like tens, like 30 million years. So for now it's still difficult. I didn't find validation, but it's my direction to go on the erosion rate and depositional rate. I can only find some modeling results for now.
And do you think there's also local variations in precipitation rates because of your tectonic history?
Yes, there should be local variations, as the orographic effects is something we need to consider about on the rift flanks. So yeah, if it's it could be considering the 3D model. It would be more great to have that. But in this one, we didn't take that part.
Great, thanks.
Thank you.
Yes, Renee.
Yes, I actually have a question, but before I do that, I want to hijack the time and just announce that I've seen quite a lot of interaction in the chat, and maybe you saw something that you want to ask the author about during this meeting. And I thought it would be useful to advertise that we have a messaging channel in a software called Element that you can use similar to Slack to contact other people. Quite a lot of the Aspect users are already in that channel because we are using that for our hackathons. So if you want to contact anyone specifically, then that's one way if you don't know their email or don't know how to contact them otherwise. I'll put that in the Zoom chat and also a link to our forum where you can also ask questions. But now to my actual question, and that was for Helia. So your model is on a pretty small scale and also very short time scales. And I don't know, maybe I missed it, but do you consider elastic deformation in your model? And do you think it's important? Because oftentimes this is a length scale where we would expect that some sort of elastic deformation also happens, right? So I don't know if this is relevant for your case or if it doesn't matter or if you already include it. That's essentially my question. What about elastic deformations on your model time and spatial scales?
I didn't consider the elastic deformation. Actually, I only included the viscoplastic behavior. Yeah. Well, it was more about the time that I had to develop the model. No, I had the idea to do in a time-dependent scale. And in that way, I would need to consider the elastic part.
Yep. I could have a quick note here. I suggested to Argelia we wait until we're done with the new VE print with the new viscoelasticity formulation to start on that.
Okay,
I thought, yeah.
Yeah.
Great.
All right. Thank you.
Yes. I'm Prajakta.
Hi. A great talk, Liang and Arjun. So first question, like I have for Liang. So, like you said about like weak zone strength and all. So for that, like we see the deeper and wider oblique rift basins, which are parallel to the rift axis, right? So, I was just wondering that why the asymmetric thing, why asymmetric basin we are seeing? Like, is it like is it totally dependent on the strain migration or like or erosion or sedimentation? Like that's my question. Yeah, for you.
Yeah, the result of even without any of the surface processes, we can still see the asymmetric patterns because we have the oblique rifting. The application of the strain will change more from like orthogonal, the normal sleeve to like strike sleeve to certain portion. That's why you can see in the north portion and south portion we have this wider and asymmetric patterns of the rift basin. But the role of surface processes would enhance or discourage it to a certain degree. So I don't know if that answers the question. Yes, because of the obliquity, that's why it looks. It also depends on the rheology of the lithosphere and also the weak zone strengths, all those things. But we need to consider surface processes another contributor to that geometry of the basin.
Okay. Yeah, thank you. And I have one question for Arji as well. When you were defining the faults in your models, like did you so I just want to know like what was the impact of the deep angle of the faults on in your model as it grows, yeah, or in time?
So I'm not pretty sure or yeah about how to answer that because I didn't vary like the dip of the falls, no, like because I already know like which dip did they have. I started by doing that, but at sometimes just for testing like some models, I remember by varying like a 5 to 10 degrees. I didn't see like a difference in the deformation pattern or the distribution. But maybe because I finished the models with the dip that I present, I couldn't say like, oh, if I really had a huge variation or not.
Yeah, but like in my some of my models, I see the deflection and everything, depending on the deep angle. So that's why I was interested to know. Like, yeah, thank you.
Great. Dave.
Yeah, thanks first off to all the speakers for the really interesting talks. It's been great to see. My questions for Liang, I was wondering about this conclusion that the low erosion models have sort of a higher frictional strength because of the development of the topography adjacent to the rift, and maybe it leads to this jumping of the like extension along the structure that's parallel to the rift margin to something that's kind of perpendicular to the extension direction. And I was wondering whether you could test that by, for instance, looking at the area of the fault and its orientation, and then considering like with the additional topography, whether the force on the structure, the additional pressure from the topography would be enough to make it favorable to jump to a structure that is shorter in terms of its total length, but a new structure that's in the middle of the rift margin. I'm just curious whether you have thought about that or if you could comment.
Thank you, David. I didn't thought about that. I'm just worrying about the validation for that hypothesis. It's actually a really good idea. Yes, this is a good point. Maybe it can be tested and find some locations with this setting to test that. Great, thank you, David.
Yeah, you're welcome.
Do we have any other questions for the speakers? Hey, if not, then this is perfect timing. We're at halfway through the hour. We'll The next step will be to take a 30-minute break, and then the afternoon session at this same link, it'll be time for open questions, technical discussions. Renee, did you want to say anything briefly before we take the break, or would anyone else like to make any announcements?
Just briefly about the next session. So this part is unstructured. There's no program. The idea is that if you have questions that you want to ask of the speakers or of someone else, then that's another opportunity to ask those questions. Or if you have other questions about model setup, technical problems, whatever, that's the time to ask them. But if you don't have any of these questions, then don't feel pressured to stay around and show up for that session. Otherwise, the ordinary part of the program will continue tomorrow.